So, insert. Let me write the code again. Okay, insertion also has two main cases. There's this case and the other case. There's no else here. This happens in both cases. And then there's some just annoying little details at the beginning. Just like over here, we had to check for the min specially. Here, we've got to update the min and max. And there's a special case, which I haven't mentioned yet. v.min will be, special cases, it will be this value none if the whole structure is empty. So this is another way to tell whether a structure, or is the obvious way to tell whether a structure is empty, it has no min. Because if there's any items in there, there's going to be one in the min slot. So first thing we do is check, is our structure empty? If it's empty, the min and the max become the inserted item, we're done. So that's the easy case. We do not store it recursively in any of the, in here. That's what this means, that this element does not get stored in any of the clusters. If it's not the very first item, or it's not the min item, then we're going to recursively insert it into a cluster. So we always insert, if we have x in cluster C, we always insert index I into cluster C. That's except if it's the min. Okay, now it could be where a structure is non-empty, there is a min item there, but we are less than the min. In that case, where the new min, we just swap those, and now we have to recursively insert the old min into the rest of the structure. So that's a simple case. Then we also have to update v.max just in the obvious way. This is the easy way to maintain a v.max invariant. That is the maximum item. Okay, now we have the two cases. I mean, this is really the obvious thing to get to do insertion. We have to update the summary structure, meaning if the cluster that we are inserting into, cluster C, is empty, that means it was not yet in the summary structure. We need to put it in there. So we just insert C into v.summary. Pretty obvious. And in all cases, we insert our item into cluster C. This looks bad, however, because there's two recursions in some cases. If this if doesn't hold, it's one recursion, everything's fine. So if the cluster was already in use, great. This is one recursion. This is constant work. We're done. The worry is if the cluster was empty before, then this insertion is a whole recursion. That's scary because we can't afford a second recursion. But it's all okay because if we do this recursion, that means that this cluster was empty, which means in this recursion we fall into this very first case. Right? That structure, its min is none. That's what we just checked for. If it's none, we do constant work and stop. So everything's okay. If we recurse in the summary structure, this recursion will be a shallow recursion, just does one thing. You could actually put this code into the else case if you preferred, or sorry, into this if case, and make this an else case. That's another way to write the code. But this will be a very short recursion. So either you just do this recursion, which could be expensive, or you just do this one, in which case we know this one is cheap. If this happens, we know this will take constant time. So in both cases, we get this recursion, square root of u plus constant, and so we get log u insertion. Do you want to see delete? I mean, it's basically the same thing. It's in the notes. You do the obvious thing, which is you delete in the cluster, And then if it became empty, you also have to delete in the summary structure. So there's, again, a chance that you do 2 recursions, but, well, okay, I'm talking about it. Maybe I'll write a little bit of the code. I think I won't write all the code, though, just the main stuff. So if we want to delete, then basically we delete in cluster C, index I, and then if the cluster has become empty as a result of that, then we have to delete cluster C from the summary structure so that our predecessor and successor queries actually still work. Okay, so that's the bulk of the code. I mean, that's where the action happens. And the worry would be, in this if case, we're doing 2 recursive deletes. The claim is, if we do this second delete, which is potentially expensive, this one was really cheap. The claim is that emptying a Van M de Boas structure takes constant time. Like if you're deleting the last element. Why? Because when you're deleting the last element, it's in the min right here. There's nothing, everything below it, all the recursive structures will be empty if there's only one item, because it will be right here. You can check that from the insertion. If it was empty, all we did was change v.min and v.max. So the inverse, which I won't write here, is just to clear out v.min and v.max. So if this ends up happening, this only took constant time. You don't have to recurse when you're deleting the last item. So in either case, you're really only doing 1 deep recursion. So you get the same recurrence and you get log u. So for the details, check out the notes. I want to go to other perspectives of Van M de Boas. This is one way to think about it. And amusingly, and this is probably the most taught way to do Van M de Boas, it's in CLRS described this way because in 2001 when I first came here, I presented Van M de Boas like this in the undergrad algorithms class with more details. You guys are grads, so I did it like 3 times faster than I would in 6046. But and then, so now it's in textbooks and whatnot. But this is not how Van M de Boas presented this data structure. Just out of historical interest, this is a way that I believe was invented by Michael Bender and Martin Farch Colton, who are the co-authors on cache fluvius B-trees. And around 2001, they were looking at lots of old data structures and simplifying them. And I think this is a very clean, simple way to think about Van M de Boas. But I want to tell you the other way, which is the way it originally appeared in their papers. There's actually 3 papers by Van M de Boas about this structure. Many papers appear twice, once in a conference, once in a journal. This one, there's 3 relevant papers. There's conference version, journal version. The only weird thing there is that the conference version has 1 author, Van M de Boas. The journal version has 3 authors, Van M de Boas, Kaas, and Zylstra. And they're acknowledged in the conference version, so I guess they helped even more. In particular, they, I think, implemented this data structure for the first time. It's a really easy data structure to implement and very fast. Then there's a 3rd paper by Van M de Boas only in a journal which improves the space a little bit. So we'll see a little bit what that's about. But what I like about both of these papers is they offer a simpler way to get this, to get log u predecessor. Let's not worry about insertions and deletions for a little bit and take what I'll call the simple tree view. So I'm going to draw a picture. 0, 1, 0, 0, 0, 0, 0. Okay. This is what we call a bit vector. Meaning here's item 0, item 1, item 2, and here is u minus 1. And I'll put a 1 if that element is in my set and a 0 otherwise. Okay, so 1 is in the set, 9 I think is in the set, 10, and 15 are in the set. I kind of want to maintain this. This is, of course, easy to maintain by insertions and deletions. I just flip a bit on or off. But I want to be able to do successor queries. And if I want the successor of, say, this 0, finding the next one, I don't want to have to walk down. That would take order U time. Very bad. So obvious thing to do is build a tree on this thing. And I'm going to put in here the OR of the two children. Every node will store the OR of its children. Okay, and then keep building the tree. Okay, now we have a binary tree with bits on the vertices. And I claim if I want to compute the successor of this item, I can do it in a pretty natural way in log U time. So keep in mind this height here is W, right? Log U. So I need to achieve log W. So of course you could try just walking down this tree or walking up and then back down. That would take order W time. That's like the obvious BST approach. I want to do log W. So how do I do it? I'm going to binary search on the height. How could I binary search on the height? Well, if you look at what I really like to do in some sense, if I look at the path of this node to the root. Where's my red chalk? So here's the path to the root. Okay, these bits are saying, is there anybody down here? Right? That's what the OR gives you. So it's like the summary structure. If I want to search for this guy, well, if I walked up, eventually I find a 1. And that's when I find the first nearby element. Now in this case, it's not the successor I find, it's really the predecessor I found. When you get to the first one, the transition from 0 to 1, you look at your sibling, the other child of that 1, and down in this subtree, there will be either the predecessor or the successor. In this case, we got the predecessor because it was to the left. We take the max element in there, and that's the predecessor of this item. If instead we had found this was our first one, then we look over here, take the min. There's, of course, nothing here, but in that situation, the min over there would be our successor. So we can't guarantee which one we find, but we will find either the predecessor or the successor if we could find the first transition from 0 to 1. And we can do that via binary search because this string is monotone. It's a whole bunch of zeros for a while, and then once you hit a 1, it's going to continue to be 1 because those are OR. That 1 will propagate up. Okay. So this is the new idea to get log U predecessor successor is to, let's say, any root to leaf path is monotone. It's 0 for a while, and then it becomes 1 forever. So we should be able to binary search for the 0 to 1 transition. And it either looks like this, or it looks like this. So our query was somewhere down here in the 0 part. I'm assuming that our query is not a 1, otherwise it's an immediate 0 to 1 transition. And that's a special case. It's easy to deal with. And then there's the other tree, the sibling of x, the other child of the 1. And in this case, we want to take the min, and that will give us our successor of x. And in this case, we want to take the max over here, and that will give us the predecessor of x. So as long as we have min and max of subtrees, this is constant time. We find either the predecessor or the successor. Now, how do I get the other one? Pretty easy. Just store a linked list of all the items in order. So I'm going to store a pointer from this one to this one, and vice versa, and this one to this one. This is actually really easy to maintain, because when you insert, if you can compute the predecessor and the successor, you can just stick it in the linked list. That's really easy. We know how to do that in constant time. So once you do this, it's enough to find one of them, as long as you know which one it is, because then you just follow a pointer, either a forward or a backward pointer, you get the other one. So whichever one you wanted, you find both the predecessor and successor at the cost of finding either one. So that's a cute little trick. This is hard to maintain dynamically at the moment, but this is, I think, where the Van Ende-Boos structure came from. It's nice to think about it in the tree view. Now let me, so we get log u predecessor and successor. I should say what this relies on is the ability to binary search on any root to node path. Now, there aren't enough pointers to do that. So you have a choice. Either you realize, oh, this is a bunch of bits in a complete binary tree, so I can store them sequentially in an array, and given a particular node position in that array, I can compute what is the second ancestor or the fourth ancestor or whatever in constant time. I just do some arithmetic and I can compute from here where to go to there. It's like the heap, regular old heaps, but a little bit embellished because you have to divide by a larger power of 2, not just one of them. So that's one way to do it. So in a RAM, that all works fine. When Van Ende-Boos wrote this paper, though, the RAM didn't kind of existed. It just wasn't as well developed then. And the hot thing at the time was the pointer machine. And their data structure, or I guess at that point they called it the Pascal machine, more or less. Pascal does have arrays, and the funny thing is Van Ende-Boos does use arrays, but mostly it's pointers, and you can get rid of the arrays from their structure. And essentially, in the end, Van Ende-Boos, as presented like this, is in a pointer machine. Let me tell you a little bit about that. So, call this original Van Ende-Boos, which I'll call stratified trees. That's what he called it. It's basically this tree structure with a lot more pointers. So in particular, each leaf, or every node actually, let's say, stores a pointer to the 2 to the ith ancestor, where I is 0, 1 up to w, I guess? No, log w. This is the 2 to the here. So once you get, the ancestor immediately above me, 2 steps above me, 4 steps above me, 8 steps above me. That's what I really need to do this binary search. The first thing I need is halfway up. And then if I have to go down, I'm going to need a quarter of the way up. And if I have to go down, I want an eighth of the way up. Whenever I go up, if I decide, oh, this is a 0, I've got to go above here, then I do the same thing from here. I want to go halfway up from here, from this node. So as long as every node knows how to go up by any power of 2, we're golden. We can do binary search. The trouble with this is it increases space. This is u log w space, which is a little bit bigger than u. And the original Van Ende-Boos paper, conference and journal version, achieves this bound, not u. Little historical fun fact. Not terribly well known. Cool. So that's stratified trees. I need to say anything else? All right. Stratified tree, right. At this point, we have fast search but slow update. Let me tell you about updates in a second. Yeah, question?
So once you do the binary search and find the first one, how do you go walk back down the tree?
Oh, I didn't mention, but also every node stores min and max. So that lets me do the teleportation back down. Every node knows the min and the max of its subtree. Right, one more thing I was forgetting here. When I say this is a lot of pointers to store, you can't store them all in one node. And in the Van Ende-Boos paper, it's stored in an array. But it doesn't really need that it's an array. It could just as well be a linked list. And that's how you get pointer machine. So So this could be a linked list. And then this whole thing works in pointer machine, which is kind of neat. And it's a little weird because if you use a comparison pointer machine where all you can do is compare items, there's a lower bound of log n because you only have branching factor constant. But here the formulation of the problem is when I say give me the successor of this, I actually give you a pointer to this item. And then from there you can do all this jumping around and find your predecessor or successor. So in this world you need at least use space even to be able to specify the input. So that's kind of a limitation of the pointer machine. And you can actually show in the pointer machine log u is optimal for any data structure, predecessor data structure in the pointer machine. So there's a matching lower bound log u in this model. And you need to use space, so it's not very exciting. What we like is the word RAM. There we can reduce space to n. And that's what I want to do next, I believe. Almost next. One more mention. Actual stratified trees, I mean, here we got query fast, update slow. Stratified trees actually do update fast as well. Essentially, it's this idea, plus you don't recursively store them in, which, of course, makes all these bits no longer accurate. It gets much messier. But in the end, it's doing exactly the same thing as this recursion. In fact, you can draw the picture. It is this part up here, the top half of the tree. This is summary. And each of these bottom halves is a cluster. And there's root U clusters down here. So those are smaller structures, and there's one root U cluster up here, which is, or one root U size Van MWS structure, which is a summary structure. These bits here are really it's the bit vector representation of the summary structure. Is there anyone in this cluster? Is there anyone in this cluster? And so on. This, of course, also looks a lot like the Van MWS layout. Take a binary tree, cut it in half, do the top, recursively do the bottom. So that's why it's called the Van MWS layout, is this picture. Okay, but if you take this tree structure and then you don't recursively store mins and then the bits are not quite accurate, it's messy. And so stratified trees, if you try to read the original paper, it's a mess. Whereas this code, pretty clean. And so once you say, oh, I'm just going to store all these clusters as an array and not worry about keeping track of the tree, it actually gets a lot easier. And that was the Bender Farch Colton cleaning up, which never appeared in print, but it's appeared in lecture notes all over the place. And now CLRS. Cool. I want to tell you about two more things. It's actually going to get easier the more time we spend with this data structure. All right. We draw a box. At this point, we've seen a clean way to get Van MWS. And we've seen a cute way in a tree to get search fast, but update slow. I want to talk a little more about that. Let's suppose I have this data structure. It achieves log W query, which is fast, but it only achieves W update, which is slow. Right, how do you update the structure? You update one bit at the bottom, and then you've got to update all the bits up the path. So you spend W time to do an update over here. If updates are slow, I just want to do less updates. We have a trick for doing this, which is you put little things down here of size theta W. And then only one item from here gets promoted into the top structure. We only end up having n over W items up here, and about 1 over W as many updates. If I want to do an insertion, I do a search here to figure out which of these little, call these chunks, which little chunk it belongs in. I do an insert there. If that structure gets too big, it's bigger than, say, 2 times W or 4 times W, whatever, then I'll split it. And if I delete from something and gets too small, I'll merge with a neighbor, maybe resplit, just like B trees. And We've done this many times by now. So then, but only when it splits or I do a merge do I have to do an update up here. Only when the set of chunks changes do I need to do a single insertion or deletion up here, or constant number. So this update time goes down by a factor of W. But I still have to pay whatever the update cost is here. So what do I do with this data structure? I don't want to use Van de Boas because this could be over a big universe, who knows what. I use the binary search tree. Here I can afford a binary search tree because then it's only log W. Log W is the bound we're trying to get. So you can do these binary search trees. It's trivial. Just do insert, delete, search. Everything will be log W. Okay, so if I want to do a search, I search through here, which conveniently is already fast, log W. And then I do a search through here, which is also log W. So it's nice and balanced. Everything's log W. Down here, if I want to do an insertion, I do an insertion here. If it splits, I do an insertion here. But that order W update cost, I charge to the order W updates I would have had to do in this chunk before it got split. So this is our good friend indirection technique we will use over and over in this class. Very helpful when you're almost at the right bound. And it's actually in the follow-up Van de Boas paper. A similar indirection trick is in there. So we can charge the order W update in top to, that's the cost of the update, to the order W updates that have actually been performed in the bottom. Because when somebody gets split, it's nice in its average state, or when it gets merged, it's going to be close to its average state. You have to do a lot of insertions or deletions to get it out of whack and cause a split or a merge. So, boom. This means the updates become log W. Searches are also log W. So we've got Van de Boas again in a new way. Bonus points. If you take this structure, which, okay, right, even this structure, if we did it in the array form, great, it was order U space. If we did it with all these pointers and we wanted a pointer machine data structure, we needed U log W space. But this indirection trick, you can also get rid of the log W in space factor. It's a little less obvious, but you take this, here we reduced N by a factor of W. You can also reduce U by a factor of W. I'll just wave my hands. That's possible. So U gets a little bit smaller. And so when we pay U log W space, if U got smaller by a factor of W, this basically disappears. So you get at most order U space. Okay, but order U is not order N. I want order N space, darn it. So let's reduce space. As I said, this is going to get easier and easier. By the end, we will have very little of a data structure, but still we'll have log U. And you thought this was easy, but wait, there's more. Okay, right now we have two ways to get log U, query and order U space. There's the one I'm erasing, and there's this, take this tree structure with the very simple pointers, add indirection. So admittedly, it's more complicated to implement, but conceptually it's super simple. It's like do this obvious tree binary search on the level thing, and then add indirection, and it fixes all your bounds magically. So conceptually very simple. Practically, you definitely want to do this much simpler. Now, what about saving space? Okay, very simple idea, which I think again comes from Michael Bender, Martin Farch, Colton. Don't store empty structures. Okay, so in this picture, we had an array of all the clusters, but a cluster could be entirely empty, like this one. This is an entirely empty cluster. Don't store it. It's a waste. If you store them all, you're going to spend order U space. If you don't store them all, just don't store the empty ones, I claim your order N space. Done. So I'm going back to the structure I erased. Ignore the tree perspective for a while. Don't store empty clusters. Okay, now this sounds easy, but in reality it's a little bit more annoying because we wanted to have an array of clusters so we could quickly find the cluster. if you store an array, you're going to spend at least square root of u space, because at the very beginning, you say, here are my root u clusters. Now, some of them might be null pointers, but I can't afford to store that entire array of clusters. So don't use an array. Use a perfect hash table. So v.cluster, instead of being an array, is now, let's say, dynamic perfect hashing. And I'm going to use the version which I did not present. The version I presented, which is universal hashing, was order 1 expected, but we know, or I said that it can be constant with high probability per operation. It's a little bit stronger. So now, I mean, everything's fine. If I do an index v.cluster c, that's still constant time with high probability now. And I claim this structure is now order n space. Why is it order n space? By simple amortization, charge each table entry in that hash table to the min of the cluster. Right? Every time, we're only storing non-empty ones. So if one of these guys exists in the hash table, we had to store a pointer to it, then that means the summary structure is non-zero. It means this guy is non-empty. So it has an item in its min. Charge the space up here to store the pointer to that min guy. Then each min item only gets charged once, because it only has one parent that has a pointer to it. So you only charge once, and therefore charge and table entry only charged each element once. And that means, and that's all your space. So that's order n space. Done. Kind of crazy. I guess if you want, there's also the pointer to the summary structure. You could charge that to your own min, so then you're charging twice. But it's constant per item. So this is kind of funny. Again, doesn't appear in print anywhere, except maybe as an exercise in CLRS now. But you get linear order n space just by adding hashing in the obvious way. Now, for whatever reason, Willard didn't see this or wanted to do his own thing, and so he found another way to do order n space log u query with hashing. Okay, but if you just take Van den Bosch of any, well, I guess also you had to think of it in this simple form. It's harder to do this in the tree. It can be done, I think, but this is a simpler view than the tree, I think. And then, boom, order n space. But it turns out there's another way to do it. This is a completely different way to do Van den Bosch. Actually, not that completely different. It's another way to do this, and with hashing. And this is what's called, I'm going to start with what's called XFast trees, and then we will modify it to get YFast trees. That's Willard's terminology. Okay, so XFast trees is store this tree, but don't store the zeros. So don't store zeros, only store the ones in the, we call this the simple tree view. This is why I in particular wanted to tell you about the simple tree view, because it is really what XFast trees do. So what do I mean by only store the ones? Well, think of them, each of these ones has sort of a name. What is the name of this item? Its name is 1, or in other words, 0001. Each of these nodes, you can think of what is the path to get here. Like the path to get to this one is 100. 1 means right, 0 means left. Those names give you the binary indicator of where that node is in the tree, in some sense. So store the ones as binary strings in a hash table. Again, a dynamic perfect hash table. Let's say get constant with high probability. Okay, and if you're a little concerned, so what this means, the ones are exactly the prefixes of the paths to each of the items, right? This was item 1, and so I want to store this one, which is empty string, this one which is 0, this one which is 00, this one which is 000, this one which is 0001. So it's, I take 0001, which is the item I want to store, And there's all these prefixes, which are the items I want to store. And for this really to make sense, you also need the length of the string. I mean, strings of different lengths should be in different worlds. And so the way actually XFAST trees originally did it in the papers have a different hash table for strings of different lengths. So that's probably an easier way to think about it. You store all the items themselves in a hash table. You store all the prefixes of all but the last bit in a separate hash table, all but the last 2 bits in a separate hash table, and so on. Now, what does this let you do? It lets you do this. Binary search for the 0 to 1 transition. Right? What we did here was, I look at the bit, is it 0 or 1? Instead of doing that, you do a query into the hash table and say, is it in the hash table? It's in the hash table if and only if it is 1. So looking at a bit in this conceptual tree is the same thing as checking for containment in this hash table. But now we don't have to store the zeros, which is cool. We can now do search, predecessor or successor, fast, in log W time, via this old thing. Okay, again, you have to have min and max pointers as well. Okay, so in this hash table, you store the min and the max of your subtree. Or actually, from a 1, you actually need the max of the left subtree, and you need the min of the right subtree. Okay, but it's a constant amount of information per thing. This is not perfect, however, in that it uses NW space, and also updates are slow. It's order W updates. But we're almost there, because we have fast queries, slow updates, not optimal space. Take this, add in direction. Done. And that's Y-fast trees. Y-fast trees, you take X-fast trees, you add this indirection right here, and you get log W per operation, order n space. Of course, this is with high probability because using hashing. Because we have factor W bad here, factor W bad here. You divide by W, you're done. Up here you have n over W space, n over W times W is n. Queries, just like before, remain log W. But now, boom, updates. We've paid log W because of the binary search trees at the bottom, but pretty cool. Isn't that neat? I've never seen this before. I mean, okay, I've seen X-fast trees and Y-fast trees, but it's really just the same. We're taking Van M. de Bois, looking at it in the tree view. You can see where Willard got this stuff, right? It's like, oh man, I really want to store all these bits, but hey, it's way too big. Just don't store the zeros. That means we should use a hash table. Hash table just gives you whether the bit is in or out. Great. Now use indirection. And indirection was already floating around as a concept at the time. Slightly different parameters. Van M. de Bois had his own indirection to reduce the space from U times log W to U. But Willard did it, and boom, got down to n space in this way. But as you saw, you can also do it directly to Van M. de Bois. I mean, all these ideas can be interchanged. You can combine any data structure you want with any space-saving trick you want, with indirection if you need to speed things up and reduce space a little bit. So there's many, many ways to do this, but in the end you get log W per operation order n space. And that is sort of result 1. It's probably the most useful predecessor data structure in general. But next time we'll see fusion trees, which are good for when W is huge.